a PhD in ocean physics from ETH Zurich in Switzerland. He then spent some time working at British Antarctic Survey in Cambridge before coming to Princeton to do a postdoc. Alex has general interest in Southern Ocean ocean physics, in particular the recent freshwater imbalance in the Southern Ocean Antarctic shelf.
Great. So shall I just go ahead?
Yeah, I think so.
Great, great. So yeah, welcome everyone, and thanks for inviting me to give this presentation. It's very nice to talk to you all, and also thanks, Craig, for organizing this very nice webinar series. I've been enjoying it so far when I was able to join. Just up front, I don't know if you please feel free to just interrupt me if you have any questions along the way. I prefer being interrupted and have asked questions in between, because sometimes when you sit in front of your computer and you're just talking to your screen, it feels a bit lonely, and sometimes you don't even realize whether people are still there. So I appreciate being interrupted if you have any questions. So as Craig said, I'm working at Princeton University, and I'm mostly looking into questions around freshwater fluxes in the Southern Ocean stratification and changes over time. So this talk will be kind of a summary of things that I've been doing during my PhD, but also some more recent work. So maybe first a quick introduction. Why am I looking at freshwater fluxes in the Southern Ocean? First of all, we know that surface fluxes in the Southern Ocean in general, so both freshwater and heat, but also momentum, are very poorly constrained often, which is associated with observational challenges that we have in this area, but also associated with the very complex nature of these fluxes. A lot of fluxes are associated with ice-ocean, ice-atmosphere interaction. There are a lot of feedbacks involved. So you can see just some of these fluxes being illustrated here in this overview from a paper from Bourassa in 2013. But it is very important to better understand these fluxes and the impact that they have on the Southern Ocean, because they are critical for better constraining and understanding the response of the global carbon cycle, the surface warming and cooling globally, and also the sea level rise. So let's have a closer look at the Southern Ocean. This is just a schematic of the Southern Ocean here, and Antarctica in the middle, the sea ice here in the shading, and the ACC, the Antarctic Circumpolar Current. And then this cake diagram is kind of cut open, where you can see down into the ocean, and you see the overturning circulation in the Southern Ocean, with bottom water formation along the continental margin, and this northward Ekman transport here at the surface, which then also results in a subduction of Antarctic intermediate and mold waters here. So why are we looking at freshwater fluxes in particular in the Southern Ocean? For this, if we zoom in here and look at the structure of temperature and salinity in the profile, we can see that the high latitude is very different from the low latitudes. So the low latitudes, as most of you dealing with oceanography know well, are determined by this very strong thermocline here. So the very strong temperature stratification, whereas the high latitudes, which I refer to as being south of the Antarctic Circumpolar Current, are dominated by a very cold surface, and actually it's colder at the surface than it is at the subsurface. So by itself, this means that there is actually an unstable vertical density stratification induced by temperature. But overall, the density stratification is stable, and that is due to the salinity. So we look at the zonal mean vertical salinity profile, we can see that the surface, which is very cold, is also very fresh. So we have this tongue of low salinity waters here at the surface that also gets subducted here with the Antarctic intermediate waters, and are a very distinct signature of Southern Ocean high latitude waters. So it's important to understand this salinity, this low salinity tongue here, and also how it's changing over time and what drives it, to better understand how this whole circulation works and what sets up the stratification in this region. So another way of looking at this is dividing the global ocean into something that's called an alpha, beta, and transition region ocean, whereas the alpha refers to the ocean that's determined by temperature stratification, and here alpha refers to the thermal expansion coefficient, and the beta ocean is the one that's driven by salinity stratification. So you can see really that these polar regions are the one that are driven by salinity stratification, and there is this transition region in between that's also important. And this extends even further north if you look at the subsurface. So this beta ocean that's induced in the high latitude Southern Ocean also extends with the Antarctic intermediate water even towards almost the equator here in the Atlantic. So we can also look at this in a seasonal cycle, this difference in the salinity and temperature stratification in the Southern Ocean. This is just from a model, a regional ocean model. We are just looking at this region here in the South Pacific. And we can look at this by season. So this goes from January, here is summer, to winter, July, August, September, and then back to summer here in December. And the black line is the total n squared. So this is a measure of the stratification in the surface ocean. And you can see that it's really stably stratified here in summer, and then it gets marginally stratified in winter. And if we look at what causes this stratification to be stable or not so stable, we can split this up into the contribution by temperature and salinity. And then the green one is the salinity-driven stratification, and the red curve is the temperature-driven stratification. So in summer, they are both positive when there is heating of the surface and there's freshwater input into the surface. So both tend to stabilize the surface ocean. And then as we go to winter, the temperature starts destabilizing. And actually, as I said before, as I showed you before, it turns the surface ocean into something that's not stratified by temperature anymore, but only stratified by salinity. And the salinity always dominates over the temperature, which makes it marginally stable. So it's really a wintertime effect that we are seeing here. So what kind of freshwater fluxes are there in the Southern Ocean? As they are so important, we have to consider them separately as well to better understand how they're changing. So we have the precipitation and evaporation fluxes from the atmosphere, which you can get estimates from, for example, atmospheric reanalysis data. Then we have the land ice, so that the ice sheet, which contributes freshwater to the Southern Ocean through melting of ice shelves along the margin and melting of icebergs. And then there is the sea ice cover, which is here in red, which is seasonal ice cover that forms and melts every season. And that was kind of the main focus of my research so far. And it does provide a very strong surface freshwater flux. So the total area that is covered by the sea ice in the Southern Ocean is about the same size as the US and Canada together when it is at its maximum extent in winter, and then melts back again almost completely in summer. So what is the freshwater flux from sea ice? As the sea ice forms, you can see this in this very nice movie that was taken under the sea ice around Antarctica. It rejects the salt. So this is called brine, and this very salty solution is being rejected to the ocean, and what is left behind is almost freshwater. So the salinity of sea ice is about 6 to 8 PSU or gram per kilogram, and the salinity of the ocean is around 34, as you know. So we have been looking at quantifying this flux from sea ice. For this, we used satellite observations of sea ice concentration and sea ice drift. And we combined this with model reanalysis data of sea ice thickness, as well as a few observations of ice thickness that we have from space as well, to estimate these fluxes between 1982 and 2008 using a mass balance approach. Doing this gives us the following result. So on the left, what you see is sea ice freshwater fluxes that are associated with the ice formation. So this rejection of the salt, basically, that you saw in this video just before. And on the right, you see the sea ice freshwater fluxes that are associated with the melting of ice in summer. As you can see already, that actually the spatial patterns of these are not fully the same. So the sea ice formation mostly happens here at the coast, and the melting is more spread out and actually is strongest further out from the coast. So if you combine these two pictures, what you get is the net annual ice ocean freshwater flux that's associated with ice melting and freezing. And it is non-zero spatial in certain regions because of the advection of the ice, so the transport of the ice. So what we can see in this picture is that there are basically two regions of main sea ice transport. So one of them is the Weddell Sea here, where you have very strong ice formation at the coast and then an export to the open ocean where it melts in summer. And the other region is here, the Ross Sea, where the same happens, and they are about the same in terms of strength. Not too much happens here in the other regions, even though there is also a tendency for the ice being exported northward. A lot of this ice export to the north happens due to the mean ocean circulation. So you have here the Weddell Sea gyre and here the Ross Sea gyre, as well as the atmospheric, the climatological wind directions in the atmosphere. So often we have low pressure systems sitting here over the Weddell Sea that transport the ice in this direction, as well as here in the Ross Sea, where there is the Amundsen Sea low that also tends to transport the ice northward in this region. So we kind of compared these fluxes to existing fluxes from land ice and from the atmosphere. There are a couple of papers estimating the land ice melting at the base of the ice sheets, as well as the melting from icebergs or the calving fluxes. And there's also publications that actually look into the distribution of these melting icebergs. So we combined these studies to come up with estimates of how these actually enter the surface ocean, and then combined this with era interim atmospheric reanalysis data to compare them to the atmospheric fluxes. And we added in our sea ice fluxes here. So we split up the ocean or the high latitude Southern Ocean, which is south of the ACC here, which is the Subantarctic Front here, the northern boundary, into the coastal ocean and the open ocean. The coastal ocean is, the division between these two regions is the zero sea ice freshwater flux line that you saw in the previous graph. So it's this black line here, which is the net zero ice ocean flux from sea ice. Here in the coastal ocean, what you can see in terms of the fluxes, the sea ice freezing fluxes are the largest term, strongly extracting freshwater from the ocean. Then there's some ice melting, and the difference between the two is the net northward transport, which is this 130 millisweater up here. Then there is the land ice basal melting, and some iceberg melting along the coast, as well as the atmospheric excess of precipitation over evaporation. if you sum all these terms up, you end up with almost net zero balance, which is interesting because this also explains you to some extent why this circumpolar deep water, the upwells here below the sea ice, has approximately a similar salinity to the Antarctic bottom water that sinks here along the coast. So if we switch over to the open ocean, in the open ocean, this balance is a little bit different. So you have a small sea ice freezing term, which is ice that's being formed offshore. Then you have a very strong sea ice melting term, which is the dominant term here. Icebergs that drift further out, and the stronger contribution by the atmosphere. And the sum of these adds up to a very strong net freshwater input to the surface ocean, which explains why we have this very low salinity tongue here in the high latitude Southern Ocean surface waters that spreads on and subducts with Antarctic intermediate water. Another way of looking at this is to look at isotope data. So oxygen isotopes that you can measure in seawater are actually a very good tracer of the surface freshwater fluxes. You can see this here in this graph illustrated that in the atmosphere, the oxygen delta 18O gets depleted as you go southward because the heavy isotopes, the O18, tends to rain out first. So it gets more and more depleted as you go further south, giving a very low oxygen isotope signal for the glacial ice, so the precipitation that accumulates on the Antarctic ice sheet. Whereas, for example, the sea ice fluxes of freshwater do not change the isotopic signature so much. So there is a very small fractionation associated with ice formation, but compared to the meteoric signal, it's very small. So by looking at small variations in the oxygen isotopes in the seawater, as well as salinity, you can actually tell where these fluxes are coming from. So it's some sort of fingerprint of these surface freshwater fluxes. So what we have done is we have collected a huge data set of oxygen isotope data at the surface on two main expeditions. So one was from the Antarctic Circumpolar expedition in 2016-17, and one was from the British Orchestra cruises here in the South Atlantic. And so I split this data set up into 3 different regions. Region 1 is all the data that you see here in orange, which is north of the Subantarctic Front, which is this gray line here. So north of this region, all the surface waters show a tendency of getting more and more depleted in the oxygen isotope values as you go further to the south, which has to do exactly with this southward depletion of the precipitation signature in the oxygen isotope values. And also, so does the salinity. There is some regional variations which makes up this spread in that you can see here. And it kind of overlaps with the Subantarctic Front here because this is the zonal mean position, right? So it kind of goes back and forth meridionally as you go around. So it's all the data that's north of the Subantarctic Front, but it's just the mean position here for illustration. So as we look at the data that was collected south of the Subantarctic Front, we noticed that there is a substantial change in the behavior of the oxygen isotope and also the salinity. It actually flattens out very much. So there is not too much meridional variation anymore as you go further south. There is a bit more in the salinity, but not so much in the oxygen isotopes. So why is that? One reason is the ocean circulation. We know that the ocean circulation that I showed you in the very beginning in the picture is in a way that you upwell waters here in the south, and then these are being transported northward through the northward Ekman transport and are being subducted here around the Subantarctic Front. So here you have kind of a convergence of surface waters that come from the north, which are these orange ones, and waters that come from the south. And these waters here from the south are permanently renewed. So the surface residence time is not that long as these waters in the north that can accumulate the signal from the atmosphere very long. So this is one of the reasons. Another reason that I will go into in a little bit is the sea ice formation. But first, I want to show you the last bit of these. I said it would be 3 regions. So the third region is a bit hard to see, is data that was collected along the continental margins or in waters that are very shallow, which are the green dots. And these are typically next to glaciers. So here, for example, South Georgia are these samples here that were collected next to melting glaciers at South Georgia. So you can see that there are very strong coastal signals in these water samples here that are somewhat different from the open ocean signals. So to better understand this and the processes that are going on, we plot this in the oxygen isotope versus salinity space values. And first of all, again, the data to the north here in orange is very much driven by precipitation evaporation. So it nicely falls on this very confined line here that you can draw a regression through. And as you go to lower values, there tends to be more precipitation. As you go to higher values, there is more evaporation. One surprising thing is that when we saw this, that this is very confined to this very distinct line, and it doesn't really depend on the basin that you're in. We've collected data from 3 different basins, and they all fall onto the same line. So you could see that in this plot here, they were still quite a bit scattered, which came from the different basins. But if you plot salinity versus isotope data, then the relationship is very unique. As we go further to the south, these blue samples here, you can see that their scatter in this diagonal direction is much smaller, and they have a large scatter here along the x-axis, so in salinity, but not so much in the oxygen isotope data. And this is exactly, the reason for this is the sea ice formation. So as I said before, sea ice doesn't affect the oxygen isotope data as much as it affects the salinity. So if it forms and melts, you can have huge changes in salinity, but these changes in oxygen isotope are rather small. You can get this signal of sea ice melting and freezing from ice cores. So these are sea ice cores that were taken here on this cruise in the Atlantic, where you can see that this is the sea ice data when you exclude the snow layers. And this is the oxygen isotope data of the water just below. So this is this dashed line here, which is the oxygen isotope signal of ice formation and melting along this line. And then the green dots, they kind of fall on both axes, right? So the coastal samples. So there is some sea ice spread here from sea ice melting and freezing, but there is also this spread that is kind of an extension of this orange line towards much lower values, which are associated with the melting of the glaciers. So you can nicely see this 3 different freshwater fluxes in this diagram. So what we learned from this overall is that the precipitation evaporation seem to dominate the freshwater fluxes north of the Subantarctic Front, and then there's quite a sharp change to the polar waters to the south of it, where sea ice melting and freezing are an important driver. And if you come close to the coast, it's also the glacial meltwater fluxes that are an important driver of salinity changes. So in the last part of this talk, I want to go a little bit into trends in the Southern Ocean, so multi-decadal changes. For this, you can see here the similar cake diagram that I showed you in the beginning for temperature and salinity, but this time it's not the zonal mean temperature and salinity, but their changes over time. So these are changes from 1982 to 2011. You can see a lot of the signals that are being discussed extensively in literature, where you can see, for example, this cooling of this high latitude Southern Ocean surface here, a warming below, and you can see also a distinct warming to the north of the Antarctic circumpolar current. At the same time, we see that the high latitude surface ocean gets fresher. There is a freshening around the coast and a freshening of Antarctic intermediate and mode waters that we see here as well. So why is this change happening, and why is the Southern Ocean actually cooling despite global surface ocean warming? There are a couple of mechanisms that have been suggested in literature. One that has an effect on the Southern Ocean temperature changes is the delayed Southern Ocean surface warming due to its mean circulation. So the idea of this is that you upwell constantly waters from the deep ocean that haven't seen the global surface ocean warming yet. So these waters haven't been affected by anthropogenic changes in the surface heat fluxes that much. So they kind of replace the Southern Ocean surface waters all the time, and so these waters here do not get the chance to heat up as quickly as the other waters. This can explain why the warming here is delayed, but it cannot explain the cooling. So for the cooling, another hypothesis is that the increasing westerly winds and the associated increase in the SAM index causes an increase in the northward econ transport that pulls more of these very cold and fresh surface waters in the Southern Ocean high latitudes to the north. One issue with this hypothesis is that if you do this in global climate models, the timescales that you can observe the cooling over are very different depending on the model. So often cooling can arise within for a couple of years when you strengthen the winds. But it's very rare that this happens over multiple decades, such as this time period that we are looking here at historically. What happens often when you do this, that it actually changes to a warming because the waters at the subsurface are at some point being pulled more to the surface, and these are actually warmer than the surface waters. So after a while, this surface ocean starts to warm as well. The third reason that was more and more explored recently is changes in the surface freshwater fluxes. And as I've been trying to convince you in the first part of this talk, is that the surface freshwater fluxes are very important in setting up the stratification and driving the density structure in the high latitudes. So you can imagine that if you change the freshwater fluxes in the high latitudes, that this has quite a strong effect also on the vertical structure of the ocean. This is not new. There have been a lot of studies that looked at different inputs of freshwater fluxes into the Southern Ocean. So some studies looked at increasing precipitation. Some studies looked at increasing melting of Antarctica, and Craig has a very nice recent paper on this, that this can have a strong effect in a global climate model. Also, the recent papers by Bronzelar et al. Have been looking into that have been discussed also, I think, in Steve Griffith's talk a couple of weeks ago. So there are a lot of model studies that show that if you put in fresh water into the Southern Ocean, then the surface starts cooling. So we tried to explore this a little bit more in a regional ocean model. And the goal was to actually directly compare different fluxes rather than just looking at one, and actually trying to make this as realistic as possible. So we did this regional setup of the UCL ETH version of ROMS, which is a regional ocean model. And the main difference to other models is that we actually constrain the model at the surface with fluxes. So there are no bulk formulas for those that are modeling it among you. We prescribe the fluxes at the surface, and not only the atmosphere ocean fluxes, but also there is no sea ice model. And the sea ice fluxes are simply those that I showed you in the very beginning of this talk from the satellite study that we did. So we prescribed these ocean sea ice freshwater fluxes and heat fluxes of latent heat and sensible heat as well. And also the land ice fluxes are distributed along the coast according to where the ice shelves are and how they are melting at the subsurface. So they're distributed vertically, and also the heat fluxes associated with the land ice melting. So then we run a couple of perturbation experiments with this model. One of the perturbations are the changes in the sea ice fluxes that we observed from 1982 to 2008. And you can see that most of the change here happens in the Pacific. So here where we had this strong northward export of sea ice, this northward export of the sea ice strengthened over this period that we are looking at, and substantially strengthened this northward transport of freshwater by sea ice. The reasons for this are also, we think we understand this, is mostly a strengthening of the Amundsen silo in this area that tends to push the ice out from the continental shelf to the open ocean. The opposite kind of happened here in the Weddell Sea, where this was slightly weakened, this northward transport. You can see also soon that the model response to that is also zonally asymmetric. So there's a different response in the Pacific than there is in the Atlantic. The second perturbation is land ice perturbation. So we took these fluxes from Paolo of grounding line changes, as well as ice shelf thickness changes, excuse me, as well as the changes in the grounding line, and estimated an increased land ice input that approximately doubled from around the early 90s to more recent years. And we imposed that perturbation on a model as well. The third perturbation that we imposed is momentum fluxes. So it's pure atmosphere ocean momentum fluxes. It's not affecting the sea ice at all. So the motivation of this is to see how this hypothesis of increased northbound Egmont transport could also cause the changes in the hydrography of the Southern Ocean that we see. So let me show you the response of the model. These are again the observed changes that I showed you in this cake diagram in the beginning, just one on top of the other. So on top you see the salinity change. Blue is the freshening, so you can see this freshening tongue in the high latitudes at the surface. And below is the temperature change, so you can see this cooling at the surface and this warming at the subsurface. So the response of the model to the sea ice freshwater flux changes gives you a very similar picture in quite a lot of regions. So you can see this very distinct surface freshening here that we also have in the observations that spreads to the north. You can also see a cooling at the surface and a warming at the subsurface due to the increased stratification associated with the salinity changes. The major difference that you can see is here along the coast, where the model does then the opposite to the observed changes, which is due to the rejection of the increased rejection of brine or the reduction in melting of sea ice along the coast. So this is kind of compensating for this increased freshwater transport northward. If we then look at the glacial meltwater experiments, where we just add glacial meltwater along the coastal margin, vertically distributed, where you can see that this causes a strong freshening, but this freshening only happens in coastal regions. So they're all kind of south of 70 degrees south, and they very much compensate for this salinity increase from the sea ice. So if you put these two pictures together, you kind of get something that's very close to these observed salinity changes. And the same is true for temperature, actually. So you get a cooling along the coast at the surface and the warming at the subsurface. And if you combine these two pictures, you get a very similar change in the vertical temperature structure. Now, the last experiment with the air sea momentum fluxes that we changed. So the purely changing ocean circulation and mixing, not changing the sea ice advection. You can see that this is kind of opposite to what we observe. So you get what I said before, over a very long time scale, which is what these model experiments are. So I forgot to say these are run for 40 years, and this is a snapshot that's averaged over year 15 to 20, I think. And so this is there you get a warming at the surface from just an increased overturning circulation, and a warming to the north here, which is actually then again consistent with the observed changes due to an increased heat uptake with increased subduction from the change in the overturning circulation. Similarly, sorry, down here is the temperature and up here is the salinity. I mixed this up. So here's the temperature. You get a warming here at the surface, a cooling at the subsurface, a warming to the north, and a salinity increase at the surface and to the north as well.
I have a question on that, Alex.
Sure.
When you said if you combine these two pictures, you sort of get the observed changes, do you just mean that you're doing that by eye, or did you also run an experiment that combined these flux changes?
That's a good question. No, I meant by eye. We didn't run combined perturbation experiments. It would be a very interesting thing to do. I just meant that if you look at just these changes as they are here, that they seem to compensate. Of course, there are non-linearities in the system. So as you combine these perturbations in a model, it might be that there's some differences in the response from just non-linearities in the model. So yeah, that's a good question. So coming back to this seasonal signal that I showed you in the beginning in terms of surface ocean stratification, it's again the same region here in the South Pacific where we saw these strong changes in sea ice transport. And the solid lines are exactly the lines that I showed you in the very beginning from this model. And the dashed lines are those from the perturbation. So as you can see is that the entire surface ocean here in the South Pacific cools, which actually tends to destratify the surface ocean. But the salinity, so from the freshwater input from the sea ice melting, is much stronger. So you can see that actually this freshening here strongly stratifies the surface ocean, which leads to a net stratification throughout the whole year in this region. This then affects the mixed layer depths. So this is the same plot for the surface ocean mixed layer depths over this region, but it's somewhat different in the response. So this is just an average over the surface ocean stratification. And what you can see here in the mixed layer depths is that if you increase the melting of sea ice, so the northward transport and the associated freshwater fluxes, then the mixed layer depth shoals in winter. So you reduce the very deep mixed layers in the winter, which leads to less intrusion of warm waters from below. So there is a cooling of the surface because there is less intrusion of warm waters that sit below the surface. At the same time, there is cooling of the surface because you have the same amount of cooling of the surface layer, but over a much shallower layer. So these the cooling is kind of trapped in a shallower mixed layer. And also at the same time, you don't mix the cold waters down, right? So one further interesting aspect of this sea ice experiment is the trapping of the heat at the subsurface. And this is now also relevant to the topic of the seminar series, which is the sea level change.
Why?
Sorry? Was there a question?
Accidental. I'm just gonna Sorry, please continue.
Okay. So here what you can see on the left is observed changes in the subsurface heat content. So these are heat content changes between 100 meters and 2000 meters depths from observations. And you can see that, of course, there is a strong increase in the heat content here north of the Subantarctic Front due to increased uptake of anthropogenic heat. But there is also an accumulation of heat at the subsurface here in circumpolar deep water to the south. And we get a very similar picture of this trapping of heat at depths when we do the sea ice experiment. So we can also see that there is an increase in heat at depths here along West Antarctica. So there is one blob here in the central Weddell Sea, and then there is this trapping of heat here along the margin of the Amundsen Sea and Bellingshausen Sea coast and the Antarctic Peninsula, which also then spreads into the Atlantic here. And this is somewhat similar to what we observe. We also compared this heat accumulation over the time of the simulation with the glacial meltwater flux and wind perturbations. And what we find is that really this increased stratification and trapping of heat at depths from the sea ice changes seems to be quite large. And it also seems to be very close to the observations after some years of integration after the perturbation has been imposed, which is this dashed line here. So this can potentially affect ice shelf melting. So sea ice changes could actually indirectly affect the melting of the ice sheets. And then also that these changes actually probably contributed to a slowdown of the global surface warming by retaining heat at depths and increasing the global ocean heat content by about 8%, if you take into account how much this is compared to the entire global ocean heat content change.
Alex, I have another question on
Yeah,
this.
sure. Go ahead.
Do you know why the sign of the change, the heat content change from the sea ice experiment is the same in the Ross and the Weddell basins, even though the sea ice flux change was of a different sign in those basins?
Yeah, so yeah, it's actually very interesting to observe this. So what you can see is that there are kind of two different sources of this subsurface heat content change, right? One is the one that originates from the Pacific and kind of spreads over into the Atlantic, which is this tongue here, which comes from this increased stratification and increased freshwater export. So this is mostly due to a stabilization of the water column here in the southeastern Pacific. And this other blob here originates from the reduction in the ice export from the Weddell Sea. So here you had more fresher water along the coast because the export was reduced, but it wasn't as much as the one in the Pacific. But it seems that both of them cause a warming, and this reduction doesn't really compensate much here for a decrease in the heat content or a destabilization. So that also shows that probably the spatial patterns of these are probably important, and the spatial patterns of where the heat sits at the subsurface. So we know that here is the main region of North Atlantic deep water upwelling, and this is the main region of Indo-Pacific deep water upwelling. So these are different water masses, and they sit in different locations in the Southern Ocean. So to sum up briefly, in the first part, I tried to convince you that precipitation and evaporation fluxes dominate the surface freshwater flux balance to the north of the Subantarctic Front, to the north of the ACC. But freshwater fluxes are much more important south of the Subantarctic Front, and there the sea ice freshwater fluxes drive the open ocean salinity changes and the mean salinity, and glacial meltwater fluxes and sea ice fluxes as well seem to dominate the coastal ocean salinity. And the glacial meltwater signals seem to be, at least in our model experiments and in the isotope data, to be very confined to the coastal ocean and do not spread so much in the open ocean, which happens in many of the global climate models when you impose freshwater flux perturbations that we talked about in some of the previous seminars. So the sea ice processes are very critical in separating the global surface from the ocean waters from the bottom waters and for the ocean circulation. And the oxygen isotope data can be used to understand the relative contributions of the hydrological cycle, so E minus P, as well as fluxes from the cryosphere, from sea ice, and from glacial meltwater, and the changes associated with the overturning circulation. These measurements can also be used to monitor long-term changes in the Southern Ocean. So one of the projects that we want to do in moving forward is to compile historical oxygen isotope data to better understand these changes. They are very critical for global ocean heat and carbon budgets. In the second part, where I talked about the changes, I tried to explain you why the Southern Ocean has been cooling at the surface and warming at the subsurface over this observational period from the 80s to 2011. We looked at this using factorial model experiments, and we found that the sea ice freshwater fluxes seem to be the cause for the surface cooling and freshening and subsurface warming south of the Subantarctic Front here. And the glacial meltwater fluxes are also important, but they are mostly confined to the coastal ocean, where they cause a freshening and surface cooling and subsurface warming. So a very similar signal to the sea ice changes. The ocean circulation changes that are associated with air-sea momentum fluxes, so northward Ekman transport and mixing, appear to be opposite to what we observe in the high latitudes, but they probably contributed to changes north of the Subantarctic Front. One comment that I would like to make here as well is that we did not look at surface flux changes from evaporation and precipitation in these model experiments, because these changes are very poorly constrained. So if you look at different reanalysis products that we use to force the surface ocean, many of the reanalysis products even disagree on the sign of E minus P changes in the Southern Ocean. So error interim that we used here is considered typically one of the more robust estimates in these terms, but the changes that we got from this by running such an experiment were very small compared to the sea ice changes, and also occurring further to the north. So this also speaks to what we see here in the oxygen isotope data, that precipitation changes are mostly affecting the northern part of the ACC rather than the southern part. But this is very uncertain still. So the implications of this is that sea ice related changes in the surface ocean stratification in the high latitudes can lead to a very strong subsurface warming around West Antarctica that potentially affect ice shelf melting. And that this subsurface warming also traps heat at depths, which causes a slowdown of this global warming at the surface and increase the global ocean heat content by about 8% in these small simulations. So with this, I would like to thank you, and I'm happy to answer any further questions if there are any.
Thanks very much, Alex, for that really interesting talk. Do we have any questions from you?
This is Max. I have a question. So the satellite estimates of the freshwater fluxes that you mentioned very early on in your talk. So those are using coverage information, but are they also somehow estimating volume or sea ice thickness?
Yeah, that's a good question. It's very hard to estimate sea ice thickness from space, and there is no long-term record for this.
Yeah.
There is estimates from a satellite that's called ISAT, where NASA also has the second version of it now in space. So it's ISAT-2, and there's a lot of hope in ISAT-2 to actually get this better. There was the first campaign, which we used. So we used this data. But of course, this doesn't cover a whole lot of years. So we used a model that is assimilating sea ice in the model. So it's an ocean reanalysis product to use the ice thickness from this model and the changes in ice thickness over time. And then we corrected the model data for biases using the ISAT data. So it's kind of the climatological mean looks more like the ISAT data, and the temporal evolution looks more like the reanalysis product. So we also did a lot of calculations to look into the sensitivity, whether actually these changes that we observed are mostly changes in ice thickness or are mostly changes in ice transport. So for this, we just assumed we run the same budget calculation using a mean thickness and change the ice drift over time. So this gives you almost the same result as we got. So it's mostly changes in the ice drift that caused this, which is also reassuring because we don't have as much information about the thickness.
Thank you. Yes, you answered my follow-up question, which is that the trend is not too sensitive to the assumptions about the ice thickness.
Exactly. So most of the trend comes from the drift. There is some contribution from the thickness. So also the ice that is exported more in the Ross Sea also got thicker in this model from the reanalysis, which is something that we don't really know whether it's true or not, but it's not the dominant signal.
Thank you.
We have another question from Gavin.
Hi. I understand from the setup that you use that, in this situation, sea ice changes are a forcing. But in the real world, they're very much the tail, not the dog. So do you have any insight from this into what's caused the sea ice to change in the way that it has?
Yeah, so let me try to jump to one backup slide that I have. So here are changes in atmospheric circulation. Oh, what happened here? What you can see here is the mean atmospheric circulation. So here is this Amundsen sea low that I was mentioning, and the vectors are the winds. And you can see that this circulation change is kind of asymmetric, right? So in the Pacific, the pressure change is very much a deepening of the pressure, which led to this kind of northerly winds here over the peninsula and the southerly winds here over the Ross Sea. So we think that a lot of this increased sea ice export here comes from this change in the atmospheric circulation over this time, increasing northward export of the sea ice. And so indirectly, it is a wind response, but we do not go the way in a model that we use a sea ice model that we impose a wind change on, but we separate the wind response of the ocean and the wind response of the sea ice in the model.
Yeah, but the problem with that is that the wind patterns themselves are part of the coupled system, right? So there are forced tendencies in the zonal winds that you can extract from the CMIT from the CMIT models because of the polar ozone hole. Right. So, yes. But if you impose that and you get that right, then in the CMIT models, you still don't get this change in the sea ice, right?
Yes.
So there's either something that the models are not capturing, or there's a coupling process, or there's a missing something, right?
Yeah, so it can be either a problem of the models, or it can also be multi-decadal variability, right? That plays a role here. We don't know this yet for sure. So we don't know whether these
multi-decadal variability in the so the change in the sea ice through to 2014 was outside the multi-decadal variability of all the models.
Yes.
By a significant chunk. It wasn't even close, right?
Yes.
So you're I'm not excited by that explanation, if you like.
It was just part of my explanation. I didn't finish yet.
Yeah.
So yeah, you're totally right. The multi-decadal variability isn't very captured very well either by the models. So this is not the full explanation. So the models definitely have a problem here if this is the correct interpretation of the observational data here, what I was showing. So one of the issues that we see in models more recently is that they have problems in doing the sea ice transport right. So a lot of the transport in the models happens along the coast, and it's mostly zonal rather than being meridional. So the overall sea ice budgets that you get from the CMIP5 models, they are all over the place. So that, I would say, is not very surprising that we don't see this based on how the advection and the drift of the sea ice in the models looks. That's one part that I could think of is a potential issue in the models. The other potential issues is the change in the atmospheric winds, right? So often the wind patterns that we get from the forced response in the global models is very zonal, very zonally symmetric. So you get a strengthening of the westerly winds and the southward shift. As we can see here in this picture is that over this time period, this has been much more complex. And there is arguments that either this Amundsen sea low deepening is associated with what I was saying before, multi-decadal variability, but you would also expect a similar behavior from changes in ozone depletion, right? So in the stratosphere. So there is also arguments that actually the change associated with stratospheric ozone depletion is not perfectly symmetric in a zonal sense, so that maybe it's more shifted towards the Pacific, which would then cause this zonal asymmetry, which drives the sea ice change. But it's very complex in the models, and some models have a strong response to sea ice dynamics. Others are purely responding to thermodynamic changes. So that's a very tricky question to look into.
Do we have any further questions? I'm a little conscious that those of us at GIS have another meeting to attend, so I might have to close in 5 minutes or so. Okay, thanks very much again, Alex, for your really interesting talk. I think we're going to have to head off here, but I wish everyone has a really nice rest of the day.
Thanks. Yeah, thanks everyone.
Cheers.
That's great.
Thank you. Great talk.
Thanks.